Good day, this is Dr. Ali Mugebel and we are covering Introduction to Error Control Coding. The outline of the presentation goes like that. We will start with the basic definition of error control coding, then definition of basic terminology through example, the gain and cost of using coding, Hamming distance, error control versus error detection, and then we'll look at the problem from the top. We'll look at the coding and the decoding problems. In coming videos, hopefully we'll cover coding bounds, Hamming, Gilbert, singleton bounds, and also in coming videos we plan to cover classics or classes of codes, including block codes and convolutional codes. So be with us. For the time being, we're focusing on our basic agenda, which is Introduction to Error Control Coding. When a sequence of data is transmitted or sent, it's going to be received, but unfortunately due to errors, due to the interference, noise, or what have you in the channel, some bits are not going to be received exactly. They're going to be an error. So what do? We need to solve this. So we need error control. Error control is an essential function for reliable services. One thing we can do is to use automatic repeat request, or ARQ, where we ask for a transmission. So the receiver will send or get either a positive acknowledgement or negative acknowledgement. And if we get a negative acknowledgement, it means we need to resend again. Not all applications can tolerate waiting for the transmission because we have some real-time applications. So we need to do error correction or we need to act accordingly. So error control includes error detection and or error correction. Of course, if you decide to go by ARQ, then you need to use timers and look for sequence or out of sequence arrivals. But other than that, we can use error control. We will focus on error control where we use error detection and error correction. So error detection and error correction. Let's start by understanding what do. We're going to add redundancy. We are going to repeat some data. So adding redundancy to the original data stream to enable error detection and error correction. Detection means you just detect the error. You cannot do a thing. You're not going to do anything about it. At least you know. You can ask for retransmission or take action. However, in error correction, not only that you find the error, but we can also correct it. Just to know that there are different models for the error. We can have random error. For example, if this is a sequence, if the error occurs here or wherever randomly, we call it random error. We can also have a very popular kind of error, which is the burst errors. Like this yellow bits, about 5 bits as a group, we got them in a burst of error where all of them got received incorrectly. Like zeros become ones, ones become zeros due to whatever reason. For example, due to being in the wrong location, due to deep fade in wireless communication, or due to impulsive noise or something that happened at a certain time. Now, we can also have erasers or erasers. In erasers or erasure channels, bits are lost. We know that there is something wrong. It's not just that we're receiving something and we're not sure whether it's 0 or 1. In erasers, no, we know exactly that there is something missing. So they are easier to handle relative to bits being flipped between zeros and ones. We're going to focus on errors in general, but just to let you know that there are bursts and there is, of course, random errors. So in this slide, let's focus on the basic concept of error control coding. The diagram on the right hand here shows you a binary symmetric channel, or BSC. In binary symmetric channels, we have binary transmission, 0 or 1. So because of the channel, it's going to be received as 1 or as 0. Similarly, if you send 0, you're going to receive it correctly as 0 or going to receive it as 1. So what's rho? It's the probability of doing a mistake in every bit. So small p or rho, this p means if it's usually a small number, and it shows you the probability of doing a mistake. We call it binary symmetric channel because the probability of error going from 1 to 0 is like going from 0 to 1. Of course, the sum of these two is always 1 because if you start with 0, you either get 0 or you get 1. This is called the binary symmetric channel. For such kind of channels, we can use, for example, binary repetition code. That's the simplest code we can think of. In binary repetition codes, or 3-1 codes, it means we are sending 3 bits for every single bit. So 0 will be transmitted as 0, 0, 0, and 1 is transmitted as 1, 1, 1, and hence the name repetition code, because we are repeating the same bit. Now what are we going to do is if we receive 0, 1, 1, what was transmitted? Okay, I know that all the possible scenarios are either 0, 0, 0 or 1, 1, 1. But due to the channel, I got 0, 1, 1. So what was transmitted? There are 2 scenarios. Scenario A, we have started with 1, 1, 1 with 1 error in the first location. Or there is another possibility that what we have transmitted is in fact scenario B, which is 0, 0, 0. But due to 2 errors in the second and the third location, they were flipped into 1s and we got 0, 1, 1. Which one of them is more probable is what we need to think about. So in the decoding, if you look at the probability, assuming that all bits are independent, there is no correlation if the first one is independent of the second, the third, so we can multiply the probability. Scenario A, we have one row, which is a bit in error, and we have 1 minus p, which is bit being correct, raised to power 2y, because we have 2 bits correct and 1 bit in error. However, for scenario B, it's going to be 1 minus p times p squared, because there are 2 errors here. Now we can check which of these 2 numbers are greater. Of course, for good channels where the probability is less than p is less than 0.5, we expect probability of A to be higher. Of course, if usually we deal with good channels, so p is going to be much less than 0.5, but just to give you the mathematical limit, this is going to be more probable if the condition is that p is less than 0.5. So our decoding decision will be what was transmitted is 1, 1, 1, and the one single bit is 1. So all of this is being done just to get 1 bit. This is an example we're going to build on as we go on. Error correcting codes definitions. Here in this slide, I'm going to share with you some of the key definitions. K is the number of data bits plus the number of redundant bits. For example, here we have 1 bit, which is the data, and then we have 2 redundant bits. K is 1 and R equal to 2. We are having blocks because for every single bit we are creating a block. This is called block code. There are R bits. The R bits are computed as function of the K bits. These are related. We get these 2 from here in general. And the total new length is usually we refer to it as N. There are different types of code. Some are called systematic codes. If the data appears as is exactly, we call it systematic code. If the data is not part of the sequence, we don't call it. We call it non-systematic code. We also have family of codes called linear codes, where the parity bit check bits are calculated as a linear combination of the data. That will become clear later on. So let's leave this on the side. When we come to block codes, we'll indulge more because our example is so simple for the time being. But the basic terminology that we have N bits as a coded word or code word, after which we have K bits for the information and R redundant bits. The ratio between K, the original data, and N after coding is called the code rate. So in this example, it's 1/3 code rate. In general, there are 2 raised to power K, so we have 2 possible data messages. In this example, K is 1. So we have 2 possible code words, 2 valid code words, 0, 0, 0 and 1, 1, 1. Every other one is not valid. So the possible patterns is 2 raised to power N, is 2 raised to power 3, which is 8, 0, 0, 0, 0, 0, 1, and so on. But they are not valid. The only 2 valid words are these 2. The fraction of this pattern, which is 2 raised to power K, divided by 2 raised to power N, in our case is 2 divided by 8, which is 1/4, or 2 raised to power minus 2, which is 1/4. So the fraction of used pattern is only 1/4 because we have 8 possible code words, or 8 possible code words, but only 2 are valid. So 2 divided by 8, which is 1/4. Now let's look at the same example and focus on the probability of error after decoding. So for this example, what is the probability that we will get undetected error? So there are two scenarios. Either you have two errors or three errors, because if it's one single error, we can always easily correct. We can use majority decoding. So we're saying here an error will be undetected if you have two errors, which means row to raised to the power 2 and one correct, and that have different locations because the error could be in the first two, second, or first and last. So we have choose three possibilities. And the second term here shows you the case where we have all of them are incorrect. So we have rows to the power 3 and there is only one possibility because we have 3 bits and we have choose 3, which is just 1. If we continue like this, we'll get the probability of being undetected. Alternatively, we can say that it's equal to 1 minus the probability of being correct, which is the case that we have no errors, or the case we have one single error. There are 3 locations for the error, 1 in error and 2 are correct. So we can write it this way or that way. So we need to know what is the probability of being undetected. If our code in general can correct TC errors, it can correct 2, 3, 4, 5, whatever. So probability of being correct will include no errors, 1 error, 2, up to TC, which is the maximum possible corrected number of errors. So we can do the summation like we did here, and we get the probability of being correct. If you want, of course, the undetected, it will be 1 minus this. Now, if a code word is in error, it does not mean that all the bits are in error. In our case here, we have only one single bit. So if we miss the code word, we miss the bit. So we need to distinguish between probability of being undetected or error undetected and probability of being bit error rate or probability of being a bit being in error. Because the fact that the code word had error does not mean that all bits are going to be wrong. In our example, yes, it's true because we have only one bit. But in general, probability of bit error rate or bit error rate is less than probability of being undetected error. So for this example that we had 3 to 1 repetition code for binary over the binary symmetric channel, the probability of having error in the beginning without coding, so you have 10 raised to the power minus 2, this is your row, this is coming from the channel. But after coding, if you use repetition code, this will drop. Now I get this through substitution here, just substitute for row for this example. This can change from one channel to another. For this number, it went from 1% to 3 out of 10,000. So this is the gain that we did by repetition in terms of accuracy. Of course, the cost is we have expansion in bandwidth requirement or reduction in the data rate by 1/3. So this is not a very good code because the cost is high. The Hamming distance of the code word. This nice diagram illustrates the Hamming cube. For the simple example, because we have only 3 bits, we can visualize up to 3D. So this shows you the distance between the different code words. We have 0, 0, 0. These represent the different possible received code words. The only valid in our case here is the dark blue, which is 0, 0, 0, and 1, 1, 1 for the repetition code. Now, we have a distance between these code words, but we're going to define something called the Hamming distance. The Hamming distance between two code words, code word I, code word J, or 1 and 2, we refer to that or denote that by D. The difference in Hamming code between these two code words is the number of components they differ in. For example, the number of bits. So what you do, you take these two code words, you compare them, and you can see that the difference is 1. Okay, you go from here to here by changing 1 bit. The distance is 1 bit. What you do, we XOR the two code words, and then we look at the weight, how many ones there after we XOR. So for example, if you XOR here these two, you get 0, 1, 1, and then we have the weight of 2, which means the number of ones. Similarly here, if you XOR these two, you get 1, which is the difference in the first bit only. So the Hamming distance is a measure of how many bits they differ in. So if, for example, you receive this, are you going to decode it as 111 or as 000? I know that this is not a valid code word. You look at the distance from here to here, you have 2, while from here you have 1. Any path you take, you have distance of 2. But to here you have only 1. So that is the Hamming distance. This is closer, so this is going to be decoded as 1, 1. So we can say that maximum likelihood decoding, the optimal decoding, reduces to minimum distance decoding. It's like finding the minimum distance if, of course, the zeros and 1 are equiprobable. If zeros and 1 are equiprobable, if they are not, then we cannot just do this. In many cases, many applications, they are really equiprobable. So this is about the Hamming distance. Now, for our example that we had before, the Hamming distance is, we can find the Hamming distance between any code word. For another code, which is very popular, called the 7-4 code, which means for every 4 bits, we're going to generate 7 bits. So we have, this is a sequence, because in total we have 16 different possibilities from 000 up to 111. And this is the equivalent, this is the associated code word. This is the code word for the given bits. This is called the 7-4 because we are having n equal to 7 number of bits and the incoming bits are 4. So we can also define the minimum distance. So there is a distance between this guy and this guy. There is a distance between, so between this and this, there are 3 bits, sorry, this distance is 3. And from here to here, for example, the distance is 3. You can find the distance between any of these code words. The minimum distance of a code word, C, the code word is referred to as C, is the minimum Hamming distance between any 2 different code words. So you try all of them, all combinations, and then you find the minimum, and that's called the minimum distance because it's important parameter. A code with minimum distance dmin can correct all error patterns up to and including TC error patterns, where of course I will explain this in the next slide in a second. But the beauty about daemon, it determines how many bits you can correct. It determines the strength of the code. Okay, so let's get to the second equation on the next slide. Error correcting and detection. Consider a code consisting of 2 code words with Hamming distance daemon. How many errors can this code correct? Let's say that we have 2 valid code words, and this is the distance 1, 2, 3, 4. Visually, we can see that the number of errors can be detected is dmin minus 1. So if you are here and you go here, 1, 2, 3, this still can be detected because it's not a valid. Up to dmin minus 1, but if it's dmin, it means you have already arrived to the next valid code word. So we can see the number of errors that can be detected is related to dmin by dmin minus 1. Now, the number of errors that can be corrected, okay, because you're going to find the closer one, so you have to make sure that you don't exceed the middle value. If it's odd, then we have trouble. If it's even, then we have no problem. So we're taking the floor to make sure that we are in the closer circle. So the number of errors that can be corrected should be closer to the original valid one. So it's dmin minus 1 divided by 2. Okay, and it's we're taking the floor in case we have even number for dmin. All right, now in other words, if you flip this equation back, you will find that dmin is related to the number of errors that can be corrected as 2 times tc. Tc is the number of errors that can be corrected, and td is the number of errors that can be detected. Dmin is a property of the code. Now let's take an example, error correction and detection. For this example, dmin equal to 5, so we can substitute numbers, and we can see that this error can correct up to 2 errors. It can correct up to or detect up to 4 errors. We can still be here without going into another valid code word. And if you want to combine them together, it can correct 1 error, up to 1 error, and detect up to 2 more errors. So either correction only, either detection only, and this we have the equations, or we can link them together. And in general, we can say that dmin equal to, or of course greater than, 2tc plus td plus 1, twice the correction capability plus the detection plus 1. So these formulas will help us in designing the code. What is the required dmin? Coding gain and cost. The gain is proportional to the error correction capability, how much we gain. And the cost is proportional to the number of bits that we have checked. Now, given a sequence k information digits, it's desired to add as little, as few check bits as digits as possible to correct as many errors t as possible. So what's the relation between these parameters will help us design the codes. The encoding problem and the decoding problem. Let's start with the encoding problem. Our encoding problem, we will be given k bits. So how to select 2 raised to power k code words for the code from the 2 raised to power n sequences. So if we decide to use n bits, then there are, like in this case, there is 2 raised to power n, which is 2 raised to power 7, which is how much? 128? 128 possibilities. Why did we choose only these 15? So in the coding, we would like to choose the best. How to select 2 raised to power k code words of the code C from the 2 raised to power n sequences, such that some predefined, some requirement is maximized, and the minimum distance of the code is guaranteed. So we improve the error capability, error detection or correction capability. Or on the other side, increase the minimum distance between these code words. So the question, how are the 16 code words of this example are being constructed? Is it through exhaustive search where we compare all the code words, find their minimum distance and then select? That's impossible, especially for large code words. It will be impossible to do. It will take infinite time, almost. It could be done for small code words, but not for large ones. Now, are we going to store all of these now for the coding? All those entries. We have 2 raised to power k, which is 16, n plus k. Or is there a way to do the coding easier? We'll see this in the code generation. Now, a constructive procedure for encoding is needed. I don't want to use a lookup table where you give me the code word and then I store them and I look there for them. There must be a nice way of getting the code, relating it linearly, systematically to the message. For the decoding problem, we can use a standard array where we store the data. And for example, in this scenario, we have 128 possibilities, 2 raised to power 7. And then, of course, we have those are the valid code words in red, and those are the closest in distance. So if you find any of these, if you receive any of these, you are going to decode by the standard array, by the head here. For example, if you get any of these, then it means this is the valid code word. We could do this for simple code words, but we need a constructed decoding way. We need a nice way that does not require large memory and searching in the memory. So we need to look at different type of decoders, and that's our link to our coming videos. We need to find a complete and choose the best out of the code words that we have. We need to find ways to control the distance and increase the error detection correction capability. So this is kind of our motive in the coming slides. I would rather leave you with a question or challenge. A code word of 5 bits is transmitted over a binary symmetric channel with error probability or crossover probability of 0.1. So every bit transmitted could be flipped with probability of 0.1. What is the probability that more than 3 bits will be in error? Please write your answers in the comment section, and I'm challenging you that 2 would get the same answer. Usually if it's 2 or more getting the same answer, there is a high probability that the answer is correct. Thank you for your time. We'll see you in coming videos.